If I can have your attention, please. It is 4 o'clock, so we shall begin. Our speaker today is simultaneously very easy and very hard to introduce. For many of you, you will know her on the sort of surface level positions that we see her every day as the chair of the Physics and Astronomy Department here at Sonoma State, as the head, there we go, indeed, bravo sir, as the head of the Education and Outreach Group based in the library, and in many capacities that benefit our department in so many different ways. The hard part about introducing Lynn is that her achievements are so numerous, it's very difficult to summarize. So to get some help with this, I went online and downloaded Lynn's full CV and biography, which turns out to be over 76 pages in length. So bear in mind, this is only the first 15, by the way. Sorry. Bear in mind, with that many achievements, it would be impossible for me to do justice to all of them. So let me simply say, let us give a warm welcome to Professor Lynn Cominsky.
Well, thank you very much. As some of you may know, we had the LIGO and Virgo scientific collaborations meeting here at Sonoma State all last week. So I'm pretty tired from running that meeting. But I will do my best to explain stuff about LIGO to you that you may not have heard of before. Although if you heard any of my lectures in the past year, the first half of this talk will seem boringly familiar. And then we get to the new stuff for the second half. So I will be telling you today about LIGO's discoveries of gravitational waves from merging compact binaries on behalf of the LIGO and Virgo scientific collaborations. So this was the scene a couple years ago, back in Washington, D.C., where I was very pleased to be able to be one of the people at the press conference that announced LIGO's very first results. And this is Dave Wrightsey.
We have detected gravitational waves. We did it.
All right, so that was exciting. But what are gravitational waves? So we like to refer to them as ripples in the fabric of space-time. If you consider a bunch of test mass particles that are all spread out like this in a circle, and the gravitational wave goes through, then what it does is it compresses space-time in one direction while stretching space-time in the opposite direction, and half a cycle later it reverses. Okay, so you can see that by the shape of this circle changing. But then if you put a whole bunch of those circles together into the third dimension in space-time, you can see what looks like a wave rippling through space-time. So that is probably one of the best ways I can give you to visualize something that's really a four-dimensional thing, which makes it, of course, impossible to visualize. Now, these waves travel at the speed of light, and they were predicted by Einstein in his theory of general relativity in 1915. So it's a 100-year-old prediction that was verified by LIGO's discovery of the waves, about which I will show you more. So most people, when they think of Einstein gravity, think of a picture like this, where this is the sun and this is the earth, and here is space-time represented by this fabric with grid lines on it, and you see the heavy sun warps space-time more than the lightweight earth. But this is a totally misleading picture. It's a terrible misconception. It's the only picture we can draw because we really can't draw things in 4 dimensions. Because really, if you had a mass sitting there, everything would be warped around it in all the dimensions. But we can't draw that very well. So what we draw is a sheet, and we just project the warping down into the picture of the sheet. But it's a sphere, and so the space-time is warped really in every direction towards it, really, not just underneath it. Okay, so keep that in mind when you're looking at pictures like this. They are sort of misleading. Newton, on the other hand, he thought of gravity as a force between two objects. And this is what you tend to learn in college physics classes, right? The famous Newton's law of gravitation, where the force between the two objects is the Newton's gravitational constant, the two masses, and then divided by the distance between their centers squared. And in his view, which of course, has the apocryphal story of he saw the apple fall and he saw the moon and he realized the same force was keeping the moon in orbit that caused the apple to fall to the ground, and that's probably an almost true story. But in his view, the force is transmitted instantaneously. So when you compare Newton versus Einstein, and these are little figurines that I have in my office. I like to collect Einstein figurines. This is part of my collection. So from Newton's point of view, space was flat and time was constant. But in Einstein's point of view, which is of course the correct point of view, space and time are intertwined, which is why we call it space-time. And in Newton's view, you had to have these two masses to have the force between them be what we call gravity. But in Einstein's view, you just have one mass sitting there, it's curving space-time. That curvature represents the force of gravity. Hello. And in Einstein's view, the force of gravity is instantaneous, whereas in Newton's view, the gravitational waves travel at the speed of light. So, for example, if all of a sudden the sun disappeared, we would notice that gravitational effect 8 1/3 minutes later here on Earth because we would no longer be orbiting the sun. But in Newton's view, we would notice immediately, which of course isn't true. And Newton also thought light traveled in a straight line, but we know because of the warping of space-time that light actually travels the shortest path through the curved space-time. Usually that's called a geodesic. Everybody with me so far? Okay. So, black holes. I have spent my entire career studying black holes, mostly from X-rays and gamma ray observations, in other words, using electromagnetic radiation. But black holes first became famous, or discovered, in the early 1970s. Theoretically, light cannot escape from a black hole once it crosses the magic line known as the event horizon, which is really, for a non-spinning black hole, a sphere all the way around the black hole. And the event horizon is defined by the place where if you were a particle and you were trying to escape and you were going at the speed of light and you were just outside that place, you could escape. But right at that event horizon, if you have the speed of light, you still don't get to escape and you fall into the black hole. And also, when we make stellar mass black holes, they are created by a star that starts its life maybe 30 times the mass of our sun, has a supernova at the end, the core collapses down. If the piece of the core that remains during that collapse is more than 3 times the mass of our sun, it will collapse all the way down and become a black hole. If it is less than 3 solar masses, so say around, somewhere between 1 and 3 solar masses, it will stop the collapse at what's called a neutron star, where the pressure of all of those protons and electrons that have been squeezed together to make neutrons is enough pressure to halt the further collapse. And I'm going to tell you more about black holes and neutron stars as we go through this talk. So the first black hole was one that I actually studied in my very first job after college, where I was working on data from the very first X-ray satellite, which was called Uhuru. And Cygnus X1 was a source that we observed very frequently. It was the first X-ray source discovered in the constellation Cygnus the Swan, and it was actually discovered with rocket observations in the 1960s, so before Uhuru was launched. And Cygnus X1 has a supergiant companion, so it's a black hole orbiting around a really big star that's burning matter in its core, like our sun, but much heavier. And so the black hole is orbiting the big star, and as they go around, the black hole tugs on the big star and makes it move back and forth according to this radial velocity curve here. And from analyzing these data, you can figure out what the mass is of the thing you can't see, which is the thing that's making X-rays, right? Can't see with visible light. You can see it in X-rays. And so the mass for Cygnus X1 is 16 times the mass of our sun, plus or minus about 5. And this is typical of most of the stellar mass black holes that we have observed with X-rays and gamma rays to date. We measure their masses by seeing how they tug on their companion star. The harder they tug, the more the black holes weigh. There are about 30 well-studied black holes in our galaxy. Now, another thing that happened in the 1970s, besides people deciding that Cygnus X1 was a black hole, was these two gentlemen, Joe Taylor and Russell Hulse, discovered a binary neutron star, pulsar. So this is its name, pulsar 1913 plus 16. So what we have now are two neutron stars. So each weighs 1.4 times the mass of our sun. They're orbiting each other, so it's a binary neutron star. And one of them is making pulses as it turns around, right? So it's like the cosmic lighthouse. So every time it spins around, you get another pulse, and that allows you to very accurately track the orbit of these two neutron stars around each other. So the neutron star that's pulsing is spinning around every 59 milliseconds. You get another pulse. And so when you track them, which has now been done for more years than is shown on this figure, because we're out here somewhere, keeps going, the curve, the decay of the orbit, so the orbit is shrinking, and the curve that the shrinking orbit follows is, these are the red points are the data points. This is, 25 years or something. And this is how much it's changed the period as the orbit shifts. The error bars on these red data points are smaller than the data points, and that blue line is from Einstein's theories. So you can see it's really an exact fit. Okay, so he had made a prediction that as these two objects are orbiting each other, energy will be leaving the system by the emission of gravitational waves. Those waves will carry away energy, and because the system is losing energy, the orbit shrinks. And the two stars get closer and closer together someday to coalesce and merge. Okay, so that was great. They discovered them in 1974, and about 20 years later, they got the Nobel Prize. So that was exciting for them. But this is indirect evidence for gravitational waves because you don't see the waves themselves. You're just seeing the energy leave the system. And it matches the prediction of how much energy would leave the system as being carried off by gravitational waves, the prediction being made by Einstein. Okay, now on to the more direct observations. And now I have to turn the lights down because some of these videos are sort of dark. And I'll probably turn the right one down. Okay, that's probably not bad. So this movie that I'm about to show you is not an artist's conception. It is an actual supercomputer calculation of what electromagnetic radiation, otherwise known as light, would look like from two black holes that were about to coalesce and merge. And so here we go. Okay, so notice, there are the two black holes, and you see all this lensing of all of the light from the normal stars that are around them. And then you see these little eyebrow things that are made that are actually the other black holes, light being warped all the way around. And then now they're going to merge any second now as they distort each other. There they go. And then there's one big black hole at the end, and it sort of shakes a little bit like Jell-O, and that's called the ring down, and it just sort of relaxes and settles down into its final configuration. So if you take two black holes and smash them together, you get a bigger black hole. How much bigger? Well, you'll see in a minute. Okay, so now, from the gravitational wave point of view, here are those two black holes again. This time they're just looking like points. And we have our space-time grid showing you all the gravitational waves that are being emitted as they spiral in and start to get closer and closer, and then they speed up. And the waves get stronger, and then they merge, and a big blast of waves goes out, and the bigger black hole is just left there all by itself. And of course, remember what I told you before about it's not just in this direction, it's in all the directions that this blast is going out. All right. Now, a short introduction to LIGO. So LIGO stands for Laser, Interferometer, Gravitational Wave, Observatory. So we start with a laser. This is the very simple cartoon version. It gets split by the beam splitter. The light goes to two mirrors at the ends of these long arms. That was the wave coming by. Okay, very quickly. Now we'll slow it down. There's a wave. It just got split by the beam splitter again. It's going to go down what turns out to be a 4-kilometer arm, turn around, come back again. recombine with the other wave. They add up right here. And the way LIGO is arranged, these waves are set to cancel each other exactly if there is no gravitational wave coming by. When the gravitational wave comes by and the length of the arms stretch and shrink, then you can get constructive interference, so you get a strong signal out, and then destructive interference, so you get a dark signal out, and back and forth, and we read out the signal on the final set of optics. Okay, see there they are, interfering constructively and destructively. And now it'll do it again, just in case you didn't get it the first time. This is supposed to be the greatly exaggerated gravitational wave coming through and changing the length of those arms. Okay, there's the light splitting, going down one of the arms, bouncing back, recombining at the beam splitter, out of phase. So normally we see a dark signal until the wave comes through, and then we can get some constructive interference and we can see light on the output port. All right, well that's greatly oversimplified, as you might imagine, because this is like $1 billion experiment. So we made this other video that attempts to show you a little bit of how much more complicated LIGO really is in real life. That was LIGO Hanford as seen from the air. Here's our CAD drawings. That's the control center where the laser starts out. That's what it really looks like. These are 4 kilometers long, these long vacuum lines that the laser's running through. And these things are called HAMs, horizontal axis modules. So the laser beam starts in one of them, goes through this very complicated set of optics to clean up the signal, to tune the signal, build up the power in the signal before it continues on through the next set of HAMs, which also provide seismic isolation. So this is the mode cleaner, this is the power recycling system. But this is actually pretty close to the real beam path. Here's the beam splitter that we saw in the cartoon version. It's going to go off down the 2 different arms. Now we're going to pull back so you can see what it looks like again. So these things are the HAMs. And then we go down the beam line. There's the light going down the beam line. We bounce the light back and forth about 400 times to build up the laser light in the cavity so that it's much stronger. It's called a Fabry-Perot style interferometer. And now we're going to cruise down the beam line and look at the mirror that's at the end. So everything is incredibly seismically isolated. This end test mass mirror is 40 kilograms. It's hanging by these millimeter thin glass fibers, and it's part of a 4 stages of seismic isolation that keep it from being affected by anything happening on the ground. Okay, now the beams are going to come back in, recombine at the beam splitter. Here they come. Go down to the final sets of optics, which clean the signal up again, also increase the power again. And we finally get to read the signal out at the output mode cleaner down here. And of course, this isn't even showing all the electronics. It's just showing all the optical elements. So, okay. So now the wave comes through, greatly exaggerated, and we see the arms stretching and shrinking. And then we see the light getting brighter and dimmer, and then we're going to see a signal appear as it's drawing the actual signal that we saw for the first discovery. So there you have it. There's what the real data look like, and now we're going to see more of the real data. So, okay. Now, there are 2 LIGOs. One is in Hanford, Washington, which is the flyover that we showed at the beginning of that last video. The other one's at Livingston, Louisiana, so they're sort of in opposite parts of the country. The one at Hanford, Washington is in the middle of this vast, deserted nuclear test range. The one in Livingston, Louisiana, as you can see, is in the middle of swampland and forest. If they cut a tree down in the forest, does LIGO hear it? You bet. So when you're trying to run during the daytime and there are people cutting down trees and trucking them away, LIGO sees all those signals. So it's really important to have 2 different ones that you can have a signal from, and then if the signals agree, you can believe that that was a real event. right? Getting a signal in just one of these is not good enough to convince scientists that this would be a real gravitational wave event. And so Livingston, by its very nature, because of the forest and the logging, is much noisier background during the daytime than Hanford. And so we tend to get better data from Hanford as a result during the daytime, and they're both sort of equally good at night. And they're also opposite oriented, the arms, the L of the interferometer, the arms are oriented opposite in the two interferometers. So that's another way that we can check to see if the signals are really correlated, because one is going to have the signal flipped upside down compared to the other one. And it's hard to do that with just some random noise source. And also, the fact that it takes 10 milliseconds for light to travel from Livingston to Hanford means that you can use the arrival time at the two different telescopes as a crude way to figure out what direction it came from. It's sort of like you have these two ears and you hear something, and you know, if this ear hears it louder than this ear, then you think, oh, the signal's coming from that way. And if this ear heard it first or louder, you'd think the signal's coming from that way, right? But there's a circle all the way around where you'd expect equal arrival times and equal loudness. And so you don't get very good positions with just two detectors. You just get sort of these big circles on the sky. So that will, why I explain that will be more clear in a little bit. So here are the first observations of what we were announcing at that press conference that I started the talk with. This is what we saw on September 14th, 2015. And so this is called GW 150914. So all of the gravitational wave events are named year, month, day. Okay, so, and what we've done with these two graphs, one from Livingston and one from Hanford, is we flipped one of them upside down so they would be the same, look the same as each other, and we also had to shift it by about 7 milliseconds. But you can see they both show the same pattern. The waves are getting stronger. They're also getting to be higher frequency right before the merger, and then it's over and you have the ring down. And you can see it even better in Hanford. So what is plotted here is time across the bottom. This whole thing is the last 0.2 seconds of these lives of these two black holes that are merging. And what's plotted on the y-axis is a quantity that's called strain, which is basically the percentage change in the length of the arms, or an arm. And it's not very much. It's 10 to the minus 21, or the peak strains that we measure.
Meters? So that's 10 to the minus 21 times...
Yeah, I'm going to explain that in one more slide. Okay, but first I just wanted to show you the data with the model on it. So you get your two data sets. You fit them to your numerical relativity models of what kind of signals you would expect to see from two black holes that were merging, given, you know, and then you fit for the masses of the black holes and things like that. And you can see that the data fit the model fits the data very well in both cases. They were both fitted independently, and they both gave exactly the same answers in terms of the parameters of the binary. So that was great, made everybody feel really, really great. Okay, so now back to strain. So strain is the change in the length of the arm divided by the length of the arm. And for LIGO, the length of the arm is 4 kilometers. So, and the maximum strain, as I told you, is 10 to the minus 21. So that means that each arm is changing in length by at most 4 times 10 to the minus 18 meters. That's really, really tiny, right? This is 4 1,000th the size of a proton. So much smaller even than a proton, even than a hydrogen atom, right? And you may say, well, how can you possibly measure something that's so much smaller than an actual atom? And it's because we're averaging over all of those atoms that are in those test mass mirrors. And so it works out. It's like if you were trying to measure the width of a human hair with a ruler that went to Alpha Centauri 4 light years away. Okay, that's how precise these interferometers had to be to make these measurements. And this is the sensitivity curve of the Hanford and Livingston in the two different colors as a function of frequency. So you can see here's our 10 to the minus 21. These noise spikes are all properties of the hardware, so we ignore those and we just sort of look at the bottom here. conceivably, when LIGO gets to its design sensitivity, we could see signals 100 times fainter than the one that we used in our discovery of the first black hole merger. So we've got a ways to go, and we're working on getting there. So here is what the models that were fitted to the data showed. So this is our GW 150914 binary black holes. The mass of the first black hole is basically 36 times the mass of the sun. The second one was 29. The total was 62. If you do some quick math in your head, you'll discover that leaves 3 solar masses worth of energy, like E equals mc squared energy, to be given off in the gravitational waves themselves. Okay, so 3 solar masses of mass was converted to pure energy in that merger and went out through space in all directions as the gravitational waves that we observed, which were very, very teeny disturbances by the time they got all the way to the Earth, because they were coming from 410 million parsecs away, or 1.3 billion light years away. And that's just the same thing in redshift. And also, another thing that we can measure is how fast were the black holes spinning compared to the maximum possible that black holes can spin. It's a dimensionless parameter, but they were spinning at about 2/3 of the maximum that a black hole can spin at the time that they merged. And that spin has subtle effects on the waveforms that were fitted to the data. Okay, so, yes. So since the frequency range of LIGO is 20 hertz roughly to 1,000 hertz, that actually is pretty close to the frequencies that we can hear sound waves with our ears. Our ears are sensitive in general, unless you listen to a lot of loud rock music like I did when I was young. 10 hertz to 10 kilohertz, I think my ears don't go that high. I've lost most of my high frequencies. But it's a fairly good approximation to do what we call sonifying of the waveforms. So we take the waveforms that are ripples in space-time and we turn them into sound waves so that we can experience them more fully instead of just as plots on a screen. Okay, so hopefully the volume is turned up loud enough. I'm going to play these for you, and you're going to get to listen to them. But I think it's going to be louder. Okay, so what you just heard, this is this last 0.2 seconds of the black hole's lives. This is the frequency plotted on the y-axis this time. Here's the waveform, and then this curve is what we call the spectrogram. And so it's showing you how much power there is at the frequency in the different frequencies of the waves. And remember, we said that they were getting to be higher and higher frequencies as the black holes merged. And so these spectrogram curves are going to higher and higher frequency numbers on the y-axis. And it's also getting louder, because you can see the amplitude of the waves is getting bigger here than over here. And same thing with Hanford. And so this pattern where the frequency goes up as a function of time, it goes whoop, whoop, we call that a chirp. Okay, so that pattern of increasing frequency with time is called a chirp. And I'm going to play it again. The first time you heard it, you couldn't really hear the chirpiness of it because it was in the frequencies that were actually detected. And then we shifted it up by 400 hertz so our ears could hear it better. And then it sounds more chirpy. So I'm going to play it for you again so you can hear that. Thump. Whoop. Right? You can hear the chirpy once it's shifted up a little bit. Because this one was so short at being only 0.2 seconds long for the whole event that it just sort of sounds like a thump when you hear it at the lower frequencies. But it really is a chirp, as you can see from the analysis of the data. And then I really like this cartoon that came out right after that about the birds. Okay, so obviously the New Yorker understands chirps. Go New Yorker. And we also made this beautiful graphic poster. My wonderful artist, Aurora Simonet, we were so thrilled. She won the Education and Public Outreach Award from the LIGO collaboration at the meeting last week. And so she didn't know she was getting it for all of her wonderful illustrations that she's done for LIGO over the years. So this is her putting the one waveform on top of the other waveform and then using that supercomputer simulation of the electromagnetically merging black holes to inspire her drawings of what was going on at the different parts of the waveform. So here they're still just spiraling together, and yes, they're making waves, but we can't detect them because they're too slow and too faint. And then as they begin to merge, the waves get much stronger and higher frequencies. They come into LIGO's bandpass better. And so this is the merger event, and then the ring down where the thing just sort of relaxes and quivers a little bit is afterwards. All right, that's the part of the talk that you might have heard before if you heard me talk about this a year ago. Now we're on to the new stuff. How am I doing on time? Looks good. Okay, so now, as of today, these are all of the merging black holes that LIGO has reported. So here's the first one, really big black holes. There was another one that we didn't exactly name GW because it wasn't quite statistically significant enough. So this one happened in October 12th of 2015. So we just called that one LVT for LIGO Virgo Trigger. Then we got a smaller one, and we call this the Boxing Day event. It's the day after Christmas in 2015. And then LIGO turned off for a year to try to improve its sensitivity and tweak up all the different systems. And when we turned back on again in 2017, we got this event in January, this event in June, and this event in August. So, important things to note. Remember I told you that Cygnus X1, the first black hole, the prototypical black hole of the stellar mass variety, was about 16 solar masses. Okay? Now that weight, remember, was inferred by seeing how it affected the star next to it. These masses are directly measured. These are direct measurements not only of the waves, but of the masses of the black hole. And it proves that these things really are black holes because they exactly obey Einstein's equations that describe black holes. It's not that you're just inferring it's a black hole because it has the right mass and you can't see it, and it's only making X-rays, right? These are both of these initial black holes at 29 and 36 solar masses were much bigger than anything that had ever been seen using X-ray or gamma ray astronomy from compact binaries. Of course, there's a whole other set of black holes that weigh millions and billions of times what our sun weighs that are in the centers of galaxies, but we're not talking about those kind. We're talking about the kind that were made from the end of a star's life when they went supernova. Much bigger than any black holes that we knew about in this variety. Proof that they were black holes. Of course, the one when it merged was even bigger. So to me, it was just an astonishing event. Now later we found some systems like this one and this one that are basically Cygnus X1 kind of systems. So these black holes that were made here, they're about the size of Cygnus X1. But this one was just way out of scale.
Do the arrows mean anything, or they just...
Oh, the arrows just mean that this one and this one merged and made that one. Okay, so then this one and this one merged and made that one, right? So these two made that one.
Yeah, I just meant like there's... Yeah, never mind. It was just
And
small.
and there's no particular axis here. They're just sort of in order of us detecting them and reporting them. It's not on a scale or anything. This is a scale. This is solar masses on the left. So here's our gallery that we've announced at the end of our second observing run. But even better than finding more black holes, which, you know, is incredibly cool, was the fact that we found the first merging of neutron stars. So this is now what I'm going to spend some time talking about. Halson-Taylor discovered the binary pulsar. That's two neutron stars. They will eventually merge, right? They have hundreds of millions of years to go before we see that one. But because we knew that that system existed, and we knew that neutron stars existed, because we've seen many, many neutron stars, many more than black holes, and we know that the neutron stars, when they do merge, probably make short gamma ray bursts because there's a lot of matter left over after they merge, so there's a big explosion and it heats up the matter and it makes gamma rays because it's so hot. LIGO was actually designed to look for neutron star mergers. LIGO was not designed to look for black hole mergers because A, we didn't know that they existed. We didn't have any evidence that there were two black holes orbiting each other because you can't see them unless they're orbiting another star that you're pulling matter off to make X-rays, right? So LIGO was really designed, that sensitivity curve was designed towards the higher frequencies that would be more representative of a neutron star merger. And then we would have the added benefit of, if we could see one, there should be a gamma ray burst. And so that's exactly what we saw in August. Oops, come on. Okay, so here's the chirpy thing again. And then 2 seconds later, the gamma ray burst comes out. So that was the bell. Okay, so here's the spectrogram. Now, you might have noticed that lasted a whole lot longer than those binary black hole mergers did, right? Because they were just a fraction of a second. And this doesn't even do it justice. This was just so we could put it on the same scale with the gamma ray burst. Now, Fermi, which is a satellite that I have worked on since 18 years before it was even launched, has been seeing gamma ray bursts, sees at least one gamma ray burst a day from somewhere in the sky. And it's the short gamma ray bursts that you see are probably a third of the total, the other ones being much longer gamma ray bursts that are probably from a star blowing up. But we had been hoping that someday these two fields would get together, gravitational waves and electromagnetic waves from the same source. And here it was. But Fermi routinely reports all the gamma ray bursts it sees. You don't even have to go back and look at the data. It just automatically puts notices out anytime it sees a gamma ray burst, just goes out on the internet, and all the astronomers with telescopes turn their telescopes and try to chase after it if they think it's an unusual burst. Well, you know, that's not particularly inspirational burst right there. Sort of a wimpy one, but you know, they reported it, and the information goes out right away, whereas the LIGO people have to sit and analyze the data and think about it and make sure it's real, and then they finally get around to telling people about it. So a couple hours after Fermi reported the burst, LIGO said, oh my gosh, that burst was the very same time as, you know, associated with this gravitational wave event that we've now decided is real. So in the meanwhile, as soon as LIGO said this one could be something really special because we have gravitational waves, all the people with telescopes in the whole world turned their telescopes to this part of the sky that was the error region that was identified between the intersection of the LIGO big circle and the Fermi error region, which was a big blob, and then the fact that Virgo didn't see it, which took out parts of the circle intersecting the blob. And so the very first ground-based optical telescope to get to this thing was called the SWOPE telescope. And so they named it after themselves, sort of. But it's that thing that isn't there a few days later because it's already fading away, and it wasn't there a few days before either. Something like, okay, so we wrote a paper with all the electromagnetic observations, or at least a top-level summary of them, and the gravitational wave observations, and the paper has over 3,500 authors, of which I am 2 of them, because there were so many authors they couldn't even tell that I was on the Fermi list and the LIGO list. That is about, I don't know, something like a third of all the astronomers in the entire world ended up on that paper that were involved in these 70 different ground-based telescopes that were chasing this event, that were looking at it in all the different wavelengths of the electromagnetic spectrum. So that was pretty amazing. But these guys get the credit for being there first, the SWOPE people. It's a telescope run by folks at UC Santa Cruz. And now, for NASA's PR about it. Complete with music. There's our emerging neutron stars. And then they merge, and then we have gamma rays going out, and matter being expelled. And the matter is hitting the interstellar medium and lighting up some more stuff, which then glows for a while longer. So that's the NASA animators version of that, which we used for the press conference. Okay. So what actually did we just watch happen, sort of? Did we just watch an animator's version of it happen? So we can measure the masses of the neutron stars from the waveforms, just like we did with the black holes. Turns out they reach 1.2 solar mass neutron stars. So if they merge together, they don't quite get up to that 3 solar mass magic number that would make it turn into a black hole. So I've been going around telling people for about the past 20 years that when we see a short gamma ray burst, we're seeing the birth of a black hole because 2 neutron stars have merged, and we were assuming that there would be enough mass there to make a black hole. Maybe not true. Okay, so people are still working on that, trying to figure out what exactly got made afterwards. Also, we call this the golden binary, and Aurora used goldish colors in all of this ejecta here to indicate the fact that we see evidence for what's called the R process. So you've got 2 neutron stars, they merge, you've got all these neutrons, you've got all these fragments of material. The neutrons are enriching whatever the other atoms were that were around there. And it turns out that that's how you get the heavy elements past iron. Right? So you get up to iron inside the nucleus of the regular star when it's burning elements. But to get to the heavier elements like silver and gold, and really all the other elements that are up here that are not man, don't have to be man-made, you need something like the R process. And estimates of studying the ejecta from this event showed that the R process can be responsible for at least half the heavy elements. In other words, heavier than iron all the way up through gold and platinum in the universe. Because they don't come from the reactions that are happening inside of stars like our sun or even heavier stars. Right? They had to be coming from someplace else where there was lots of neutrons around to end up in going into these atoms to get them up to be heavier than iron. So we call it the golden binary. And this wonderful illustration by Aurora was her very first Nature cover. And so she's had 2 science covers, but this was her first cover of Nature magazine with this article with all of these authors that was published in Nature. It was tremendously exciting. We announced this in October. You might remember something else that was going on around here in October. Aurora had to finish this drawing in a hotel room with her 6 cats after having been evacuated from her house, on her laptop, sneaking onto the closed campus to look at her big screen to see how the drawing was turning out. Because, she has a big graphics computer that she normally works on, right? And so she wasn't even able to go back to her house for 3 weeks, during which time she had to finish this, and the paper came out, the press conference was held, and everything. But at least when she was able to go back, her house was still there. Although the houses on the other side of the street were all gone. Her street was the fire break. Anyway, just a little personal story about how amazing this drawing is. And we now have a framed, or at least a mounted, really, really huge poster of the Nature cover that we had in a lot of our selfies and stuff from last week. The Nature people kindly gave me this big blow-up of the cover that they had made. Okay, back to the science. So, comparing the chirps from all of these events. So here's the first one, the one that was only 0.2 seconds long. Right, here are these other black holes. Okay, now we're going to show you how that compares to the neutron star chirp. Okay, so it starts, and this is really how long we saw these all for. And the time axis is just going to keep shrinking so we can see more time. So you can see how long the signal was that we got from the merging neutron star binary compared to the merging black hole binaries. All right, we're still getting there. It's still going. We're still seeing it. It's pretty strikingly different. In case you're wondering how we can tell the difference between merging neutron stars and merging black holes, I think just this little cartoon might actually be enough to demonstrate that. So it's a combination of the fact that LIGO, the sensitivity bandpass, was designed really for the merging neutron stars. But it's also because they're lighter weight, they're moving around. There it is. Okay, so 55 seconds later, we finally get the merger. But we could see all of those waves before we got to the final merger event because of the fact that LIGO was designed to focus on merging neutron stars.
If it's just masses with 2 small black holes of similar masses to, say, the most massive neutron stars also take a similar amount of time.
Right, but these neutron stars each weigh 1.2, and the latest black holes we ever saw were 15 or so.
But theoretically, the smallest limit of black holes was the highest of a neutron star.
That is true theoretically. We have just never seen any black holes that are really at around 3 solar masses. The latest ones we've really seen have been 15 or so, like Cygnus X1. So yes, if there were lighter weight black holes, you could imagine that merger would stay in the bandpass for longer. But this is really due to the fact that this is a higher frequency, and LIGO is just more sensitive at those higher frequencies. It was designed specifically for the neutron stars. Okay, so what's going on in the future? Well, LIGO right now is turned off, and I think Virgo is as well. And they're being upgraded again and, tweaked up. And this is sort of like what people do in particle physics. You run it, you see how well it's doing, you think, oh, I could fix this. I could increase the laser power. I could lower the noise in this part of the system. And then you turn it off, and then you work on all the hardware, and then you turn it back on again. And then you hope that it's better. And so it's off now for pretty much this whole year of 2018. So this talk isn't going to change again a whole lot for at least another year. And also, under construction is Kagra, which is a cryogenic interferometer in Japan, underground, because they have a lot of earthquakes there, so they were trying to get it underground to lower the seismic noise. And before, LIGO Hanford used to have 2 different interferometers. One was 2 kilometers long, and one had the 4-kilometer arms. And when they made all the hardware to do the upgrades, they were like, well, that's stupid. We don't really need 2 in this one place. If we had them in other places around the world, we could have these intersecting circles, and we could get much better positional information about where the waves came from. So the goal was to try to have one as far south as we could get, but unfortunately the Australians didn't have any money. So, and the folks from India did. And so they took the second set of detectors that the US paid for Hanford, and we're basically giving them to India. And the Indians are building all the infrastructure, all the tubes, all of the stuff you need to make it into an actual telescope or observatory. And that's happening right now. They're going great guns. We heard a report at the meeting last week. So they're buying up the land. They've done their site selection. They're working on engineering drawings. We've got all sorts of people from the US helping them to figure out how to go about building the thing. And so with any luck, maybe Kagra will be online in a couple more years, and maybe LIGO India will be online in a decade, or maybe less if we're really lucky. And then GEO is just a short little thing in Germany that's only 600 meters long, and so it's used to test out a lot of hardware, but it will never have the sensitivity to see a real signal. But wait, there's more, because just like light has a spectrum from radio waves to gamma rays, right? Low energy to high energy, long wavelength to short wavelength. So do gravitational waves. It's just that the only ones that we've seen have been the ones seen by LIGO. But there can be longer waves, for example, from even bigger black holes merging, like the supermassive black holes that are in the center of a galaxy. Those could possibly be seen with a space-based version of LIGO, which is usually called LISA, for Laser Interferometer Space Array, or possibly space antenna, depending on who's defining the acronym. And here you have 3 different satellites that are shooting laser beams between each other, and that are somehow going to know, by looking at those laser beams, what the length is of each arm before and after the wave comes through. And so it requires some tremendously sophisticated satellite station keeping, so you know where those 3 satellites are precisely enough to be able to see when the baseline has been perturbed by a very weak wave passing through. But it's going ahead. The US a long time ago was going to fund it, and then they pulled out, and now the Europeans are going ahead and building it. And a satellite called LISA Pathfinder just finished its mission, and it was testing out some of the technology for LISA. And it seemed to work, so the Europeans are going to put in a lot of money. The US will probably put in some of the money. But that's going to go ahead, although I think I'll have retired long before that ever sees launch. But this is going on right now. This is a big radio telescope, and there are a few of them all over the world. And what the big radio telescopes can do is look at millisecond pulsars. So these neutron stars, they're by themselves. They're spinning around 1,000 times a second. Very, very accurate clocks, and you've got about 35 to 50 of them scattered all over the whole sky. And by correlating the timing signals from all of these different millisecond pulsars, you should be able to see a very slow wave go by. That's called nanograv. So it's the nanohertz pulsar timing array, made up of all the biggest single dish telescopes.
So do the waves like mess with the perception of time as they come through, or?
They're basically, so if you imagine a perfect clock and you're always getting your pulses at exactly the same time, and now space got a little stretched or a little squeezed, so the pulses will be a little late or a little early because the distance that the pulses traveled to you just got changed. And so, you know, they haven't seen anything yet, but because these waves that they're looking for are very, very slow, and they've only been doing it for a couple years. But, you know, we're not giving up on them yet. And then at the very, very longest wavelengths of gravitational waves, you would see an imprint on the polarization of the cosmic microwave background. So that's what this picture is trying to show you, is all the different polarization vectors and how they're all moving around due to the gravitational waves. And so the early universe, when you had the expansion from the Big Bang, how the expansion happened would leave an imprint on the polarization of the cosmic microwave background. And if you had a really good satellite, you might be able to see that and claim that you had seen the first gravitational waves. And if you did that, you would be wrong, like the bicep people were that made that claim about 2 years ago, and about a year before LIGO found the real first gravitational waves. And then the bicep people had to retract their claim, and then they were very embarrassed because it turned out that everything they saw could be explained by dust. And so other satellite proved that. Planck was the name of the other satellite. And so, yeah, that was really embarrassing. And so because of that, we wanted to really make sure that when we published stuff from LIGO that it was really correct. And we did not publish in the press before we went through extensive refereeing process for the first papers. But we are now at the dawn of multi-messenger astronomy. So we have electromagnetic waves, we have gravitational waves, we have cosmic rays, which are charged particles. We have neutrinos, which are neutral particles. And all of these things are coming down from space and telling us something different about the universe. And if we put it all together, we can actually get a better picture of what's going on with the universe. But for my final slide, we can raise a toast to the rise of gravitational wave astronomy. Thanks to the scientists of Glasgow for creating that video.
Well, thank you.
Here's more places you can go if you want to learn more.
Excellent. Do you have questions for our speaker today?
How are we doing on time? Huh, almost exactly to the minute what I said.
How does Virgo fit into all this?
Okay, so Virgo has 3-kilometer arms, and it's in Italy. And so it's an interferometer. It's just a little bit shorter than LIGO. LIGO has 4-kilometer arms, right? So Virgo has 3-kilometer arms. But other than that, it has the advanced detectors. They had a lot of trouble with their suspensions for a while, but they've got that straightened out. So Virgo joined in the observations with LIGO in the middle of observing run number 2. And in fact, I should have said that when I showed this picture. But this was the first event that was seen by both LIGO and Virgo. So Virgo turned on in around July or August of 2017 for its first observing run. And so this was the first triple detection that was seen by both LIGOs and the one Virgo interferometer. And then after that was the next thing that happened before LIGO turned off was the merging neutron star binary, which Virgo could have seen but did not. In other words, it had the sensitivity to see it, but it did not see it, which meant that it was in one of the observationally inaccessible places on the sky for Virgo. And then those big voids helped narrow down the error region that was seen by LIGO from the circles. And then that led the people to find, that combined with the Fermi position, led the people to find the optical counterpart.
Why was the gamma ray 2 seconds later?
A very good question, and you've got a lot of theorists working on the answers to that right now.
The NASA cartoon showed the gamma rays highly directional. So how do you know the gravitational waves are totally omnidirectional?
Other than theoretically? Well, we don't have any proof, obviously. The gamma rays jets are beamed, and we know that from other kinds of observations that we do. But gravitational waves, because it is actually a perturbance of space-time itself, are by definition isotropic. Space-time is equally perturbed in all directions, not just that sheet thing. Remember, that was wrong.
I just had a couple of kind of interrelated questions. What made a LDT 15, 10, 12 not statistically able to be included with the study?
Logging at Hanford. I mean, logging at Livingston.
Fair enough.
Right, yeah. So if you go back and look at the data, that one was during the daytime in Louisiana, and there was just so much noise in the background from the logging and the trees and stuff that just wasn't. But the waveforms that you see look very convincing. It's just, you know, the collaboration is very, very picky about the statistical significance that they require in order to claim something as a real detection. And that one just failed, so they said, okay, we'll put it out there as a possible detection, but we're not going to claim that it was real. And it was the second one, so then they were like, you know, we don't want to overpromise anything, right? But then as the other ones started coming in, and they were all, you know, very good and strong, and at night, or at least in a better time with respect to logging, then people began to feel more confident.
I assume these were identified so quickly because there have been lots of simulations beforehand. What other kinds of things were simulated that have not shown up?
Okay, so you mean by identified, you mean the modeling? So how we
Yeah.
were able to find out the masses of the black holes and stuff like
What
that?
other sources, what other types of events could produce?
Oh, okay. So
produce
there,
radiation?
yeah. So there's still at least three other classes of events that we're looking for that we haven't seen yet, that are all expected to be weaker than the compact binary mergers. So there's a big group in LIGO that works on what's called CW, or continuous waves. And so that's what Ben Owen works on, one of our former students who actually did a lot of the theoretical work explaining how you would get these waves. So if you have a pulsar and it's got a little bump on it and it's rotating around, that deviation from spherical symmetry will be enough to make the gravitational waves. And what I forgot to say at the very beginning was that gravitational waves come from time-varying quadrupole moments. So if anyone's taken upper division E&M, electromagnetic waves come from time-varying dipole moments or accelerated charges, same thing. But with mass, you don't have a plus and a minus, you just have mass, right? So you need the next higher moment, which is the quadrupole moment. So two things orbiting each other have a quadrupole moment. Something that has spherical symmetry does not. So you have to break the spherical symmetry to get the quadrupole moment to vary so that you can get the gravitational waves. So if you have like a squashed neutron star, so it wasn't spherically symmetric, or a neutron star with a little bump on it, then you can generate gravitational waves at a pure frequency, the frequency of the spin of the neutron star. Not a changing frequency like a merger, where it gets faster and faster. So that's one thing. We're looking for core collapse supernovae, especially if one would go off in our galaxy. So but this, again, the supernova explosion has to be non-spherically symmetric in order for it to make gravitational waves. But most of the more sophisticated models that people make, that include hydrodynamics and stuff, have, you know, they're not perfectly spherically symmetrical, although that's the easier way to run the models. And so there's some hope for that. The same thing with the gamma ray bursts that are the long type, that come from something that's similar to a core collapse supernova that we usually call a hypernova. So if those are not spherically symmetric, you could get gravitational waves from a long gamma ray burst that would then have an electromagnetic counterpart in gamma rays that would be longer than 2 seconds. So those are the other classes of things that people are looking at. And then they're looking at the stochastic background. So that just means the random background fluctuations that you could have in gravitational wave background that could be the sum of all sorts of small things you can't individually measure. So there is a gamma ray background, there is an X-ray background. Most of those backgrounds in electromagnetic light come from distant galaxies whose individual contributions to the background we cannot resolve. So you just see it as an overall background. So people are looking for the stochastic gamma ray, stochastic gravitational wave background that could be like all these unresolved gravitational wave sources that are too far away. So those are the other things that people are looking for. I don't know if I was going to bet which one might get discovered next. Maybe You know, I'm still hoping for that close by supernova in our galaxy, because that would be a great bonanza for astronomers of any messenger. You know, we could see neutrinos, we could see electromagnetic waves, we could see more gravitational waves. It would be really, really cool.
Not too close.
Not too, not too close, but it would be nice if there was one in our galaxy.
I'm curious, so you're saying that to create these gravitational waves, you need to break the symmetry. So let's say you have two neutron stars, structures, or black holes, and there is symmetry. Does it break once they start spiraling?
No, the fact that they're orbiting around each other is
That
already a
would do enough.
quadrupole moment. Yeah,
So they treat it almost as one system, and then just that in
Yeah.
itself is
Yeah.
symmetric.
yeah. Just this motion of the two things orbiting around each other, that already is a
So
quadrupole
if you
kind of
have one
situation.
and break symmetry, you do it, or if you have two objects, you can do it.
Right, you have to have one non-spherically symmetric thing or two things orbiting each other.
And if they're different masses, that might help.
Different masses is fine too.
Yeah, I was thinking about your thought of using 35 or 50 pulsars to measure one event over long distances. Do gravitational waves, or the strength of them, or energy level dissipate over time and distance?
Yes, the waves get weaker the further they go from the source, but unlike electromagnetic radiation, where we measure the intensity, so it falls off like 1 over the distance squared, the gravitational waves only fall off like 1 over the distance, because we're actually not measuring the intensity, we're just measuring the disturbance. So they can be seen further.
Okay, as we're at 5 o'clock at this point, those of you who have extra credit are free to depart. If anyone wishes to stay for more questions afterwards, they can do so. But before we do that, let's thank our speaker again.